welcome to this problem walkthrough. In this session, we'll tackle the problem titled Number of Laser Beams in a Bank. Together, we'll explore the problem statement, break it down, and discuss the approaches to solve it efficiently. Let's dive in. In this problem, we are tasked with analyzing a security system represented as a 2D matrix called bank. Each cell in this matrix can either contain a security device, represented by the character 1, or be empty, represented by the character 0. The rows in the matrix correspond to different floors in the bank, and the columns represent the vertical alignment of rooms across these floors. A key aspect of the problem is to determine when a laser beam is emitted. A laser beam is emitted if and only if two security devices are aligned in the same column but are located on different floors, with no other security devices in between them in the same column. The objective is to compute the total number of these laser beams that can be emitted across the entire bank. The input to the problem is the bank matrix, given as a list of strings where each string represents a row. The output is a single integer representing the total count of laser beams emitted. Let's consider an example to better understand the problem. Suppose the input matrix bank is given as follows: 01100100000, 0101000, 0101000. The output for this input is 8. Let's break it down. In row 1, we have security devices located in columns 2, 3, and 6. In row 3, there are devices in columns 2, 4, and 5. Row 4 contains a single device in column 3. Notice that row 2 is completely empty, which means it does not contribute to the beam calculations but allows devices in other rows to interact. To calculate the total number of beams for this example, we consider the interactions between rows with security devices. First, between row 1 and row 3, there are 3 devices in row 1 and 3 devices in row 3. The beams emitted between these rows are calculated as 3 multiplied by 3, resulting in 9 beams. Next, between row 3 and row 4, there are 3 devices in row 3 and 1 device in row 4. The beams emitted here are calculated as 3 multiplied by 1, resulting in 3 beams. Adding these together, the total number of beams for this input is 9 plus 3, which equals 12 beams. Now, let's look at another example where the input is bank equals 000, 111, 111. In this case, the output is 0. Here's why: both row 2 and row 3 contain security devices, but there is no empty row between them. Since a laser beam requires the devices to be on different rows with no devices in between, no beams are emitted in this case. Therefore, the total number of beams is 0. Finally, let's analyze another example to solidify our understanding. Consider the input bank equals 111, 000, 111. The output here is 6. In this case, row 1 has 3 devices, and row 3 also has 3 devices. Importantly, row 2 is completely empty, which allows for laser beams to be emitted between the devices in row 1 and row 3. The total beams are calculated as 3 devices in row 1 multiplied by 3 devices in row 3, resulting in 6 beams. The output is therefore 6. Additionally, remember the constraints: the matrix can have up to 500 rows and 500 columns, and all rows are guaranteed to have the same length. Edge cases include scenarios like all rows being empty, or configurations where no beams can form due to a lack of alignment or empty rows in between devices. To begin, the brute force approach is the most straightforward way to tackle the problem. The idea is to iterate through every possible pair of rows in the bank matrix and calculate the number of laser beams by multiplying the number of security devices, represented as 1s, in those 2 rows. First, we parse the matrix row by row and count the number of 1s in each row. Then, for every pair of rows, we multiply the counts to determine the beams formed between those rows. Finally, summing up all these products gives the total number of beams. However, this approach comes with a significant trade-off. While it's simple to implement, it involves nested iterations over rows, leading to a time complexity of n squared asterisk m, where n is the number of rows and m is the number of columns. This makes it inefficient for larger matrices. On the bright side, it requires no extra space beyond the input itself, making the space complexity 1. Still, the inefficiency in handling larger datasets makes this approach less practical for real-world scenarios. Now, an optimized approach addresses the inefficiencies of the brute force method by narrowing down the rows we consider. The key insight here is that laser beams can only form between consecutive rows that contain at least one 1. Rows without any ones are irrelevant because they don't contribute to any beams. This eliminates the need to compare all pairs of rows. The process starts by pre-processing the matrix to calculate the count of ones in each row. Then, as we iterate through these counts, we focus only on consecutive rows with non-zero counts. For each of these valid pairs, we multiply the counts of ones in the two rows and add the result to our total. This significantly reduces redundant computations. The time complexity is now O, n asterisk m, since we only make a single pass through the matrix to count the ones and a linear pass through the rows to calculate the beams. Similar to the brute force method, the space complexity remains O(1), as no additional data structures are required. This optimized approach is much faster and more scalable, particularly for sparse matrices. An alternative approach could involve using a prefix sum or cumulative multiplication technique to manage rows with devices more efficiently. However, for this problem, where the focus is on consecutive rows, such an approach introduces unnecessary complexity without improving the runtime. Instead, the optimized approach stands out as the best choice. It's both intuitive and efficient, leveraging the insight that laser beams occur only between consecutive non-empty rows. This insight simplifies the computation and avoids redundant checks. Compared to the brute force approach, the optimized method eliminates unnecessary iterations, while the alternative prefix sum approach, although theoretically viable, doesn't offer any additional benefits in terms of time complexity. The optimized approach achieves O(n)(m) time complexity, making it ideal for larger inputs. It's simple to implement, requiring no additional data structures, and it handles both sparse and dense matrices effectively. Overall, it strikes the right balance between clarity and performance, making it the most practical and scalable solution for solving this problem. In this problem, we are tasked with counting the number of laser beams in a bank security system, which is represented as a binary matrix. Each row in the matrix corresponds to a floor, and a 1 in the matrix indicates the presence of a security device. Laser beams are formed between devices in different rows, but devices within the same row cannot create beams. Our goal is to calculate the total number of laser beams across all rows. To tackle this problem, we first represent the bank as a list of strings, where each string represents a row, and each character, either 1 or 0, indicates the presence or absence of a device. Then, we initialize a variable total_beams to 0, which will keep track of the cumulative count of laser beams. Next, we iterate through each row of the matrix to count the number of devices, represented as ones, using the count function. These counts are stored in a list called device_counts, making it easier to work with the data later. For example, if the input matrix is bank equals 01101000000 11,000, the device counts for each row will be 3, 0, 2. This setup is the foundation for solving the problem effectively. Now, we focus on refining the data further to make calculations more efficient. Any row with 0 devices does not contribute to the total number of laser beams, so we can remove such rows from consideration. Using the earlier example where device_counts equals 3, 0, 2, we filter out the 0 device row, resulting in the filtered list 3, 2. This step simplifies the problem by ensuring we only work with rows that can form beams. Once we have the filtered list, we calculate the number of laser beams between consecutive rows. For each pair of consecutive non-zero rows, we multiply the number of devices in the current row, denoted as prev_count, by the number of devices in the next row, cur_count. The result represents the number of beams formed between these two rows, and we add this value to total_beams. For instance, with the filtered device_counts equals 3, 2, the calculation is 3*2 equals 6. This product represents the total number of beams formed between the first and second non-zero rows. After processing all consecutive pairs, we return the final value of total_beams as the result. The logic behind multiplying device counts stems from the fact that each device in one row can connect to every device in the other row. This ensures that we account for all possible connections between two rows. To implement this algorithm, we use several data structures. The input matrix, bank, is stored as a list of strings, which makes it easy to process each row individually. The device_counts list is used to store the number of devices in each row, allowing us to focus only on relevant rows during the calculation of beams. Finally, total_beams serves as an integer accumulator that keeps track of the running total of laser beams. Analyzing the algorithm's complexity, the time complexity is primarily determined by counting the devices in each row, which takes O, n asterisk m, time, where n is the number of rows and m is the number of columns. Filtering rows takes O, n, and calculating beams for consecutive rows takes O, k, where k is the number of non-zero rows. Thus, the overall time complexity is O, n asterisk m. The space complexity is O, n, as we store the device_counts list. Key edge cases include handling an empty matrix, matrices with no devices, and situations where there's only one row with devices, as no beams can form in these scenarios. It's also important to account for sparse matrices, where many rows may have no devices, ensuring that only rows with devices are included in our calculations. Let's walk through an example to solidify our understanding. Suppose the input matrix is bank equals 01101 00000 11,000. First, we count the devices in each row, resulting in device_counts equals 3, 0, 2. Next, we filter out rows with 0 devices, leaving 3, 2. To calculate the number of laser beams, we look at the pair of consecutive rows in the filtered list. Here, there is only one pair, the first row with 3 devices and the second row with 2 devices. We calculate the beams as 3 asterisk 2 equals 6. This gives us a total of 6 beams. Since there are no other rows to consider, the final output is 6. This example highlights how the algorithm efficiently handles the problem by focusing only on relevant rows and leveraging the relationship between consecutive non-zero rows to compute the total number of beams. This Python implementation solves LeetCode problem number 2125, number of laser beams in a bank. The problem involves calculating the total number of laser beams formed between security devices in a bank represented as a binary matrix. The number of beams function works as follows. Step 1 asterisk the code first calculates the number of security devices, ones, in each row using a list comprehension. This is done with row.count, 1, for every row in the input matrix bank. The result is stored in row_device_counts. Step 2 asterisk rows with 0 devices are irrelevant because they do not contribute to forming any beams. We filter out these rows using another list comprehension, count for count in row_device_counts if count 0. The resulting list active_device_counts contains only the rows with non-zero devices. Step 3 asterisk the total number of beams is calculated by iterating through consecutive rows in active_device_counts. For each pair of rows, the beams are given by the product of the device counts in the 2 rows. The total_beams variable accumulates this sum for all such pairs. The function then returns the total number of beams as the final result. Example walkthrough. For the input bank equals 01100100000 0101000 0010000 1 row_device_counts becomes 3, 0, 2, 1. 2. Filtering out zeros gives active_device_counts equals 3, 2, 1. 3. The total number of beams is calculated as 3 times 2 close parenthesis plus open parenthesis 2 times 1 close parenthesis is equal to 6 plus 2 equals 8. This concise and efficient solution ensures that the problem is solved in linear time relative to the number of rows and columns, making it suitable for large inputs within the constraints. Here, we begin by implementing the solution to the problem in Java. The method number of beams takes an array of strings, where each string represents a row in the bank. The first step is to count the number of devices, or ones, in each row. We initialize an array called row_device_counts to store these counts. Using a loop, we iterate over each row in the bank, and for each character in the row, we check if it is equal to 1. If so, we increment the count for that row. After processing all the rows, the row_device_counts array will contain the number of devices in each row. Next, we filter out rows that have 0 devices, as they do not contribute to any laser beams. For this, we use a list called active device counts. We iterate through the row device counts array, and if a row has more than 0 devices, we add the count to the list. This ensures that only rows with active devices are considered in the next step, where we calculate the total number of beams. To do this, we initialize a variable total beams to 0 and prepare to calculate the beams by iterating through consecutive rows in the active device counts list. To calculate the total number of laser beams, we use a loop to iterate through the active device counts list. For each pair of consecutive rows, we multiply the number of devices in the current row by the number of devices in the next row. This product represents the number of beams formed between these two rows. We add this value to the total beams variable, and the loop continues until all consecutive rows have been processed. Finally, the method returns the total number of beams. In the main method, we test the implementation with a sample input 01100100000, 0101000, 0101000. The first and third rows have active devices, and the beams between them are calculated to give a total output of 8. This demonstrates how the solution works end-to-end, counting devices, filtering rows, and summing up the beams in the bank. In this example, we have a bank represented by the rows 011001, 000000, 010100, and 001000. The first step is to count the number of devices, or ones, in each row. For row 1, 011001 contains 3 devices, so we start with row _device _counts equals 3. Row 2, 000000 has no devices, so we add 0 to get row _device _counts equals 3, 0. Row 3, 010100 contains 2 devices, updating the counts to row _device _counts equals 3, 0, 2. Finally, row 4, 001000 has 1 device, resulting in row _device _counts equals 3, 0, 2, 1. Next, we filter out rows with no devices. Since row 2 has 0 devices, it is removed, leaving us with active _device _counts equals 3, 2, 1. Now we calculate the total laser beams between these active rows. Between row 1 and row 3, there are 3 devices in row 1 and 2 in row 3, so the beams are 3 * 2 equals 6. Next, between row 3 and row 4, we have 2 * 1 equals 2 beams. Adding these together gives a total of 8 beams. The output for this example is therefore 8. Here, the input bank consists of 3 rows, 000, 000, and 000. The first step is to count the devices in each row. Row 1, 000, has 0 devices, so we start with row _device _counts equals 0. Row 2, also 000, has 0 devices as well, updating the counts to row _device _counts equals 0, 0. Finally, row 3, 000, adds another 0, resulting in row _device _counts equals 0, 0, 0. Next, we filter out rows with no devices. Since all rows have 0 devices, they are all removed, leaving us with active _device _counts equals. With no active rows remaining, there are no possible beams to calculate, so the total number of beams is 0. The output for this example is 0. In this case, the input bank contains rows 111, 101, and 111. First, we count the devices in each row. Row 1, 111, has 3 devices, so we begin with row _device _counts equals 3. Row 2, 101, contains 2 devices, updating the counts to row _device _counts equals 3, 2. Finally, row 3, 111, has 3 devices, resulting in row _device _counts equals 3, 2, 3. Since all rows contain devices, no rows are removed, leaving us with active _device _counts equals 3, 2, 3. Now we calculate the total beams. Between row 1 and row 2, we multiply the counts, 3 * 2 equals 6 beams. Then, between row 2 and row 3, we calculate 2 * 3 equals 6 beams. Adding these together gives a total of 6 plus 6 equals 12 beams. The output for this example is therefore 12. Let's analyze the time complexity of solving the problem number of laser beams in a bank. The solution involves three primary steps. First, we count the number of devices in each row. This is done using the count 1 operation, which processes each character in a row. Since there are m rows and each row contains n columns, the total time complexity for this step is m*n. Second, we filter out rows that have 0 devices. This involves iterating through the row_device_counts list, which contains m elements, 1 for each row. Filtering requires a single pass through this list, so this step has a time complexity of m. Now, in the third step, we calculate the total number of laser beams. This involves iterating through that active_device_counts list, which contains the counts of devices in rows with at least one device. For each pair of consecutive rows, we compute the product of their device counts. In the worst-case scenario, where no rows are filtered out, this requires len, active_device_counts, 1 iterations, which is at most m1. Therefore, this step takes m time. When combining all three steps, the overall time complexity is dominated by the first step, which is m*n. Thus, the total time complexity of the algorithm is m*n. Now let's discuss space complexity. In the first step, we create the row_device_counts list, which stores the count of devices for each row. Since there are m rows, this requires m space. Then, in the second step, we create the active_device_counts list, which contains the device counts for rows with at least one device. In the worst case, all rows are active, so this also requires m space. The algorithm does not use any additional data structures or recursion, so the auxiliary space used is negligible. As a result, the overall space complexity is dominated by the two lists, making it m. Compared to a brute force approach, which would involve iterating through all pairs of rows and counting devices row by row, the optimized solution is significantly more efficient. The brute force approach, with a complexity of m²*n, is avoided by pre-computing device counts and filtering rows, reducing the complexity to m*n. Finally, let's analyze the algorithm's performance across different scenarios. In the best case, where all rows in the bank contain zeros, steps 1 and 2 still process all rows, leading to a time complexity of m*n. In the average case, the number of active rows, those with devices, is less than m, but the time complexity remains m*n, because step 1 dominates. In the worst case, all rows contain devices, but even then, the time complexity does not exceed m*n. This is because step 1 remains the bottleneck regardless of the number of active rows. Across all cases, the space complexity is consistently m, as it is determined by the storage of the row_device_counts and active_device_counts lists. Thus, the algorithm is both time efficient and space efficient, providing an optimized solution for this problem. When tackling this problem, there are a few common mistakes to watch out for. First, misunderstanding the input constraints is a frequent issue. For example, you might assume the matrix will always be a certain size or that it will only contain certain values, but these assumptions can lead to errors. Always make sure to clarify the constraints, such as the dimensions of the matrix and the allowed characters. This is crucial because incorrect assumptions can result in inefficient solutions or failures when dealing with edge cases. Another common pitfall is ignoring edge cases altogether. Scenarios like all rows being empty, a single row filled entirely with zeros, or even matrices with just one row can reveal flaws in your logic, such as off by 1 errors or division by 0. Lastly, be mindful of inefficient iteration. A brute force approach that compares all possible row pairs has a time complexity of n², which can be problematic for larger inputs. Optimizing your solution to handle such cases efficiently is key in both interviews and competitive programming. Another issue to watch out for is miscounting the devices in a row. While counting the number of ones might seem trivial, skipping proper validation can lead to errors. For example, failing to account for cases where rows are empty or data is sparse can produce incorrect results. It's essential to ensure your counting mechanism is robust. Additionally, overlooking alternative data structures can hinder your solution. While arrays are straightforward, using more efficient structures like hash maps or lists to store the indices of ones can significantly improve time and space efficiency, especially for sparse matrices. Now, in interviews, there are a few key insights to keep in mind. Matrix problems often revolve around recognizing patterns, such as rows or columns with specific properties. For example, pre-computing indices of ones can eliminate redundant calculations. Optimization is another crucial aspect. While brute force is a good starting point, always discuss ways to refine your approach. Interviewers also frequently test edge cases like empty matrices or single rows, so handling these gracefully is important. Lastly, make sure you're comfortable with various traversal techniques, such as row-wise or column-wise, and understand the trade-offs of each in terms of time complexity. Now let's explore some related problems that share similar concepts and can provide additional practice. LeetCode 835, Image Overlap, focuses on counting overlapping ones between two binary matrices. This problem also involves traversal and counting logic, making it a great parallel to this one. Another example is LeetCode 221, Maximal Square, which challenges you to find the largest square of ones in a binary matrix. This highlights the use of dynamic programming within a matrix context. LeetCode 240, Search a 2D Matrix 2, is another interesting problem. It emphasizes efficient matrix traversal by leveraging relationships between rows and columns in a sorted matrix. Finally, LeetCode 36, Valid Sudoku, is a classic that involves validating rows, columns, and boxes in a matrix. It's an excellent example of using hash maps and matrix traversal together. Practicing these problems can deepen your understanding of common techniques and patterns in matrix-based challenges. For this problem, there are also some alternative approaches worth considering. One method is to pre-compute the indices of ones for each row. By storing these indices ahead of time, you can avoid redundant calculations during the main logic. The trade-off here is a slight increase in memory usage, but this is generally outweighed by the time complexity improvement, particularly for sparse matrices. Another approach involves using prefix sums for rows. By pre-computing the prefix sums, you can quickly determine the count of ones between any two rows. While this adds pre-processing time, it can be advantageous for larger or more complex matrices. Finally, bit manipulation offers a creative and highly efficient solution. If the rows can be represented as binary numbers, you can use bitwise operations like AND to calculate overlapping ones rapidly. However, this method can be harder to implement and debug, so it's better suited for smaller matrices or advanced users. Each of these approaches has its trade-offs, so it's important to carefully consider the problem constraints and input size when deciding which to use. Great work on completing this problem. We reviewed the solution for number of laser beams in a bank, focusing on efficient iteration and optimization techniques. Remember the key takeaways, and practice similar problems to solidify your understanding. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!